Chapter 11 is mainly a continuation of Chapter 10. Recall, in Chapter 10 we discussed pie charts and bar graphs for displaying categorical data, as well as line graphs. In this chapter we will discuss two other graphs which apply to quantitative data. Our focus in Chapter 11 will be on histograms, stem plots, and their interpretations. Recall, bar graphs are used to display categorical data. They are relatively straightforward to construct, as each observation naturally falls into a particular category. However, this is not the case for quantitative data, as they don't necessarily fall into any category. In this case, we often group the observations into classes based on size and construct what's called a histogram. A histogram looks very similar to a bar graph. However, histograms apply only to quantitative data. To construct a histogram, we will go through the following steps. First, divide the range of the data into classes of equal width. There is no hard and fast rule for choosing the width, as the choice will vary with the context. Next, count the number of individuals in each class. This will determine the height of our rectangles. Finally, draw the histogram, being sure to label the x and y axis. Let's do an example together where we construct a histogram. Table 11.1 lists the percentage of residents aged 65 and over for each of the 50 states. Let's construct a histogram by dividing the observations into classes of length 1. The smallest observation is 7.3, and the largest observation is 17.4, so there is no need for the classes to go beyond this range. At this point, what we do is go through all 50 observations and keep track of the number in each class. For instance, for Alabama we have 13.8, so Alabama falls into the class from 13.0 to 13.9. Alaska has 7.3, so Alaska falls into the category from 7.0 to 7.9, and so on. Now once we have done this for all 50 states, we will know the height of each of the rectangles. Finally, to construct our histogram, we label the x-axis to coincide with our class intervals. The y-axis will be labeled with the number of observations. So, for the class between 7 and 8, we will draw a rectangle whose width is 1, between 7 and 8, and whose height is equal to 1. The height is equal to 1 as there is one observation in this class. For the class between 8 and 9, there will be no rectangle, as there are no observations in this class. For the class between 9 and 10, there will be a rectangle of height 1. For the class between 10 and 11, there will be a rectangle of height 3, and so on. Once we have drawn a rectangle for each class, we'll have our histogram, as shown. Now you try one. Below are the percentages of residents under the age of 18 in the 50 states. Make a histogram of the distribution following the 3 steps described in example 1. Use the following class intervals when constructing your histogram. So the class intervals in this case would be from 20 to 22, 22 to 24, 24 to 26, and so on. So pause the video and unpause when you're ready for the answer. Your histogram should look something like this. Just as in Chapter 10, our goal with constructing a histogram is to understand patterns that exist in the data. We will also look for deviations to this pattern. In particular, we will look for the presence of outliers, which are individual observations that fall outside the general trend. To see the overall pattern of a histogram, ignore any outliers. Here's a simple way to organize your thinking. To describe the overall pattern of a distribution, give the center and the spread. See if the distribution has a simple shape that you can describe in a few words. For now, describe the center of a distribution by its midpoint, the value with roughly half the observations taking smaller values and half taking larger values. Describe the spread of a distribution by giving the smallest and largest values, ignoring any outliers. For example, let's return to the histogram that we constructed in example 1. For its shape, we would say that the distribution has a single peak. It is roughly symmetric, that is, the pattern is similar on both sides of the peak. For the center, the midpoint of the distribution is close to the single peak at about 13%. In other words, about half the observations lie above 13% and about half lie below. For the spread, we would say that it's between 9% and 18%, ignoring any outliers. The following histogram lists the tuition and fees of certain Illinois colleges. This provides an example of a histogram that is not symmetric. For the shape, we would say that there is a strong peak in the lowest cost class. Most colleges charge less than $8,000, but there is a long right tail extending up to almost $40,000. If we went through and counted all the observations, we would see that the center is roughly $8,000. In other words, about half of the colleges charge less than $8,000, and about half of them charge more than $8,000. Finally, in terms of the spread, we would say that it is large, ranging from 1,974 to more than 38,000. These values can't be seen from the histogram, but they can be seen from the actual data itself. When you describe a distribution, concentrate on the main features. Look for major peaks, not for minor ups and downs in the bars of the histogram. Look for clear outliers, not just for the smallest and largest observations. Look for rough symmetry or clear skewness. Now, some terms that we will use to describe the shape of a distribution are as follows. A distribution is symmetric if the right and left sides of the histogram are approximately mirror images of each other. A distribution is skewed to the right if the right side of the histogram extends much farther out than the left side. In other words, it has a right tail. It is skewed to the left if it has a left tail. Now you try one. Figure 11.5 is a histogram of the percentages of residents aged 85 and older in the 50 states. Describe the shape, center, and spread of this distribution. Are there any outliers? So pause the video and unpause when you're ready for the answer. In this case, the single observation between 0.6 and 0.8 appears to be an outlier. The distribution is skewed right. The center seems to be somewhere between 1.8 and 2.0, as about half the observations fall below these values and about half above. The spread is from 1.2 to 3.0, again ignoring any outliers. Now, if our data set is on the smaller side, we may decide to make what's called a stem plot. Stem plots mimic much of the shape of a histogram and presents more detailed information. To construct a stem plot, we will go through the following steps. First, separate each observation into a stem consisting of all but the final digit, and a leaf, which is the final digit. Stems may have as many digits as needed, but each leaf consists of only a single digit. Write the stems in a vertical column with the smallest at the top and draw a vertical line at the right of this column. Write each leaf in the row to the right of its stem in increasing order out from the stem. Let's do an example together where we construct a stem plot. Here our data set consists of 3-digit numbers, so our stems will be of length 2 and our leaves will be of length 1. The stems will range from 10 to 26, as the smallest observation is 100 and the largest is 260. After listing each stem, we will draw a vertical line to separate them from each leaf. For each observation, we will record the last digit next to the correct stem. For instance, for 192, we will record a 2 next to the stem 19. For 152, we will record a 2 next to the stem 15. For 135, we will record a 5 next to the stem 13, and so on. We will do this for each observation in the dataset. Finally, once we have recorded each observation, we will arrange the leaves in increasing order. Let's close the lecture by making a few comments about stem plots. First, a stem plot looks like a histogram turned on end, and we interpret stem plots just like we do histograms, by looking for the overall pattern and for outliers. You can choose the classes in a histogram. The classes of a stem plot are given to you, however. You can get more flexibility though by rounding the data so that the final digit after rounding is suitable as a leaf. Do this when the data has too many digits. The chief advantage of a stem plot is that it displays the actual values of the observations. Stem plots are also faster to draw than histograms. A stem plot requires that we use the first digit or digits as stems. However, stem plots do not work well with large datasets because the stems have too many leaves.